Hello, I'm Jeroen, and together with Ruben, Gio, and Bas, we will be presenting two articles about an exoskeleton. I will start with an introduction to the two articles. Ruben will continue with the design of the device, and Gio will follow with the characterization and the control of the exoskeleton. Bas will finish the presentation with an explanation of the experiments done and a conclusion. We found two articles about an exoskeleton that is designed to acquire knowledge about the working of the human knee. The two articles are written by the same group of researchers. The first article, the design of a wearable perturbator for the human knee impedance estimation during gait, was published in 2013. And the second article, design and characterization of an exoskeleton for perturbing the knee during gait, is a follow-up and was released in 2017. The first article talks about the design methodologies and how separate components have been made and tested. The second article is about the finished exoskeleton and what they did to accomplish this. It also provides details on instrumentation and control systems. Differences between the finished product and the original concept described in the first article are also cited. The exoskeleton isn't used for the application you might think of when hearing of an exoskeleton. It is not used as an aid, but instead to gain information that can later be applied in designing exoskeletons that do help the user to walk or to make other movements. The group of researchers that have been working on the project consists of 6 people in total. Michael R. Tucker, he's the lead engineer, and he has written several other articles about exoskeletons and rehabilitation. Adrian Moser was only part of the first development group, has previously researched human health-related subjects. Oliver Lambercy, James S. Selver, and Roger Gessert all contributed to both articles, and all three have a background in engineering and robotics. Camilla Shiroda appears to have joined the team later than the others, as she wasn't part of the first article, and her interest lay in the engineering field and rehabilitation. The objective of this research was to get an improved understanding of the working of human joints. In this case, they focused on the human knee and how does the knee react to perturbations. And they want to achieve this by applying a resistance during the leg, during gait, and measure how the body reacts to these disturbances. Knowing how the joints of the human body behave both in static and dynamic situations is essential in the development of exoskeleton designs as an aid during walking. And in particular, the characterization of the knee impedance during dynamic movement is an important part of the research. Furthermore, this knowledge can be applied in the medical sector to improve treatment methods and make better diagnosis in cases involving movement disorders. There have not been any comparable studies prior to this research. The reason for this might be that there are no devices available to use for such research. I guess there are many factors like power, timing, torque, and weight that all have to be tuned together to get a representative finding. And these factors make it very difficult to create such a device. There are several tools that can be used for perturbing the leg during gait. And the researchers found that a wearable exoskeleton will be the best in applying well-timed and powerful enough perturbations to the knee. However, an exoskeleton it has its drawbacks, as it's not optimal for this kind of work. An exoskeleton has a certain weight, certain mass, and wearing it will be an unnatural experience to the user. And this might influence the findings. So in conclusion, the two articles are about the same research. They are published about the device that perturbates the human knee during gait to see how the knee reacts. And data about power, speed, torque, and timing are all collected and provide a better understanding of the mechanical impedance. And this knowledge can later be applied in the development of power prosthesis and orthoses. And the research is highly relevant because it can directly be used in the medical in the medical sector. Ruben will now continue to explain what the different design objectives and requirements are and how these parts have been designed.
Thank you for the introduction, Jeroen. My name is Ruben van Laarhoven, and as Jeroen just said, I'm going to talk to you about the design phase of the exoskeleton. The design requirements and design methodology are based on the article from 2013, and the design implementation is based on the article from 2017. The design requirements. The design team considered numerous alternative perturbation methods, but found that a treadmill suited the experiment the best, because walking on a treadmill won't differ that much from a natural walking motion. The requirements. The upper weight limit is set to 3 kilograms, and the perturbation speed is 360 degrees per second. The range of motion is 0 to 120 degrees, and the maximum allowed torque is 80 Newton meters. Next up is the design methodology. Here I'm going to talk to you about the clutch design, hinge design, and the actuator. The build of the hinge. The design team had to come up with a clever hinge design that follows the center of rotation, the moving center of rotation of the knee very precisely, so the user wouldn't experience any discomfort during gait. You can see on the right image on the screen where the construction of the hinge is based on, and you can imagine if the upper and lower leg are at an angle of each other, the cross of the hinge is not at the center of the hinge anymore. On the left image, you can see how the hinge is implemented in the final design. Next up is the clutch design. The clutch was one of the most challenging aspects to design because of its complexity. The clutch must maintain sufficient holding torque and stay within reasonable weight and size. Also, the design team had to think about the safety aspect of this part, because when it's done wrongly, it can cause injuries. In the final design, it's called a wafer disc clutch. You can see on the lowest picture on the slide that wafer disc clutch is built out of multiple thin plates, indicated with a D. When pressed together, they generate friction. When fully pressed together, the motor torque is transferred to the knee joint. Next up, also the maximum allowed torque is 80 Newton meters. Next up is the actuator. The main motor of the exoskeleton weighs about 2.1 kilograms, which is 2/3 of the maximum allowed weight. So the design team had to think carefully how to get rid of this weight. So they chose to mount the motor to an external mount, as you can see on the slide. The motor is connected to the exoskeleton with a so-called Bowden tube. Next up is the design implementation, and this part is based on the article of 2017. The final design. One big design change is made, and that is that the motor is now not connected to the exoskeleton. It's not connected to an external mount, but instead it's directly mounted to the exoskeleton with a gear reduction. Also, to save weight, the brace is made out of carbon fiber. As before, it was made out of aluminium and plastic. Apart from these changes, nothing mechanically has been changed. The intended application of the device is to provide reproducible perturbations to the knee joint of unimpaired subjects. Also, perturbations have to be distinguishable from background dynamics. In recap, I just explained the most important design aspects of the exoskeleton, the complexity of the clutch and hinge, and the placement of the motor. Gio will now present and will elaborate on the data acquisition, control design, and he will also talk in more depth about the clutch and test as well as sensing devices.
Thank you, Ruben, for your introduction. I'm Jeroen, and I'm going to talk about the controller, device characterization, and sensing and instrumentation. First, I will discuss about the controller. The knee perturbator is controlled using software developed with Simulink that executes on the controller. This controller is classified by functional units. One of the functional units is data acquisition. This function turns bad signals into reliable signals for processing. The signals that are used for control for the perturbator are digitally filtered using low-pass filters. These filters effectively remove the noise in the electricity grid. Another important functional unit is the planner. The planner is used for a number of commands, such as the list of time points where disturbances should occur, the desired disturbance amplitude, the number of repetitions to be performed in each direction, and the minimum waiting time between the disturbances. The last subject about the controller I would like to bring up is safety. For safety for the user and the perturbator contains the control software time shut off switch. This switch automatically disables the amplifier of the perturbation motor, and this prevents the motor from overheating and from being accidentally driven for a long time by a control error. In the previous slide, I talked about the controller. I will now discuss the device characterization of the wave disc clutch. One of the important parts of the perturbator is the wave disc clutch. Figure 2 shows the section view of this clutch. Ruben spoke earlier about this clutch, about how it is built, and I will discuss some important tests that have been performed on this clutch. To do these tests, they built a test setup, which you can see in figure 7. One of the tests they have done at the wave disc clutch is the holding torque. This torque determines the strength of the clutch when the motor is running while the leg don't move. They tested this by fixing the device to a test bench and running the clutch motor in steps of 10 mA. For each step, a force was manually applied to the shank of the perturbator until movement occurred at the clutch. These movements were recorded by the torque and angle sensors. When a movement occurs, the holding torque was then determined. This whole process was repeated 25 times in each direction. Another test they have done is the delay when the clutch is engaged and disengaged. While the perturbator is fixed to the test bench, the clutch is commanded to engage for 200 milliseconds and then disengage. In this way, the clutch delay of the expired time between the engage and disengage command was determined. This test was repeated 50 times. Both tests meet their requirements. In the next slide, I will talk about the sensing and instrumentation. The angular velocity of the knee and torque between the perturbator and the shank of the leg are measured using certain sensors. First, I will discuss the angular velocity and then the torque. The angular velocity is determined by differentiating the knee angle over time. The knee angle is determined by measuring the linear displacement of the coupling between the two front pins, which you can see in figure 3. To measure this displacement, a sensor was used, named string potentiometer, and it was chosen because of its compact size and ability to be remotely located. This string potentiometer consists of a standard rotary potentiometer and a constant force spring. A second string potentiometer was also designed to measure the position of the clutch rotor cylinder. The torque between the perturbator and the shank of the leg is measured using parallel strain gauges. These are mounted on the opposite sides of the crank arm, which you can see by letter G in figure 2. The signal of the gauges is filtered and amplified before it is sent to the controller. So I've told you about the most important subjects about the controller, about the important tests that were performed on the wave disc clutch, and finally about sensing and instrumentation. Now I will pass you over to Bas, who will talk about the pilot experiment and the conclusion.
Thank you, Gio. My name is Bas Holweg. To properly test the ETH knee perturbator, two pilot experiments have been done. The first experiment was done to answer the following question. Can the knee perturbator apply well-timed and reproducible perturbations during gait? A perturbation is a disturbance or an unexpected force on the knee. To test this, a group of 3 unimpaired male subjects was chosen. They walked on a treadmill set at constant self-selected speeds, and the minimum time between perturbations was set at 10 seconds, with a randomization of 0 to 5 seconds, and the direction of the perturbation was also randomized. This creates so that the user cannot expect the following perturbation. 5-degree flexion or extension perturbations were applied. That means that the leg is pushed 5 degrees in flexion or in extension and is held there for a certain amount of time. This is how the experiment was done. Now let's look at some of the results. All of the A total of 120 perturbations was done. Thank you, Gio. A total of 120 perturbations was done. In this picture, you can see the effects on the angle and the torque. In the angle, you can clearly see that the knee is moved 5 degrees in either flexion in green or extension in red, and then is held there until the end of the perturbation. The perturbation starts at 30% and ends at about 75. You can clearly see in the torque that there is an initial peak, and then it steadily increases until the end of the perturbations, when it drops back down to 0. All of the perturbations were within 10% of the onset time. The case with the largest onset time had a standard deviation of 16.3 milliseconds. This is well within the specifications. It was also said by the subjects that the device was not uncomfortable, and it was overall well tolerated by the subjects. From this, we can conclude that the ETH knee perturbator can indeed apply well-timed and reproducible perturbations during gait. The second pilot experiment was done in order to see the difference between walking with and without the knee perturbator. Again, 3 male subjects walked on a treadmill at constant self-selected speeds. They walked with and without the knee perturbator. The knee perturbator was set in passive mode with the clutch disengaged, allowing the user to walk freely. The movements were captured using external motion capture. Now let's look at the results. The only significant difference between walking with and without the knee perturbator was stride duration. This increased for 2 subjects and decreased for the third. The differences were smaller than 20 milliseconds, which is an acceptable impact. From this we can conclude that the knee perturbator does not have a significant impact on the walking cycle. To reiterate, the objective of this research was to get an improved understanding of the human knee and gait. An actuated knee exoskeleton was developed for perturbing the knee. Benchtop and human pilot experiments have shown that this device can apply well-timed and reproducible perturbations on the knee. This tool might help the development of new exoskeletons and rehabilitation methods in the future. I would like to thank you for listening to our presentation about the design and characterization of this exoskeleton.